Hello, my name is Panagiotis and I'm a PhD student at New York University where I work with Professor Sandeep Rangan at NYU Wireless. And today I'm going to present you a basic tutorial on how we can use some of the millimeter wave devices in Cosmos testbed. More specifically, in Cosmos Sandbox 1, we have a variety of millimeter wave RF frontends, such as the Sieverts 60 GHz transceiver, the IBM phased antenna array module, and two solutions from Interdigital for 28 and 60 GHz. Furthermore, we also have a variety in baseband solutions, such as the National Instruments USRP devices or some custom software-defined radios based on the Xilinx RF SoC. One of the features of Cosmos testbed is the ability that we can basically connect any baseband solution to any RF frontend. So basically this is enabled through the usage of RF switches. And as we can see on the picture on the right, more in the benchtop millimeter wave setup, we can interconnect either the USRP M310 or the ZGU111 with either the 60 GHz frontend or the 28 GHz frontend. And more specifically in this tutorial, we're basically going to focus in this connectivity. And the experimental platform, as I said, includes the Sieverts 60 GHz transceiver that it basically enables us to do some kind of like real time with high bandwidth channel measurements and recordings. The millimeter wave arrays are mounted on top of XY tables that allow us to introduce some mobility into the experiments. Using the XY table, we can move the array along the X and Y axis and rotate across the Z axis. We also provide some kind of framework that you can basically control the arrays and do some live streaming through the web cameras. Now we can go to the first demo. In the first demo, we are basically using a Python script to move the array from location A to location B. And we are also using OpenCV to do like a live streaming from the testbed. Something that is very important for millimeter wave arrays is the calibration process. And in this work, before we do any of the tutorials, we basically implemented some IQ calibration. The algorithms that we developed are based on the works of Dan and Jay, that they developed these IQ calibration mechanisms for their fully digital software-defined radio. Even though our device is phased array, these methods can be basically replicated or slightly modified to adjust to our needs. And we can see that just by fixing the phase offset at the receiver, we can basically get more than 11 dB in sideband suppression. And we can see very similar improvements after we do the TX calibration. The first example of experiments that we saw that you can run on Cosmos testbed is the channel sounding. So basically you have this simple connectivity between the RF SoC and the Sieverts, and we place the arrays in bore site, and then we measure the impulse response. To do that, we basically start two terminals. In the first terminal, we start a controller for the Sieverts array. So this is basically like a Python script that listens to this kind of HTTP API calls that is basically like moving the array. And the rest of the scripts are orchestrated from the other terminal. where you basically create the objects for controlling the FPGA, the Sieverts array, and the XY tables, and then we run the script, and you see that like here as an example is the Sieverts IQ calibration that is run, and then we apply our own like parameters to improve that. An important experiment that we can run is measuring the array response. So basically we utilize the XY table and the channel sounding to measure like the highest path along along the TX direction. So we can see that one node is placed on both sides and is measuring, and the other node is basically rotating. And for each degree of rotation, we basically like do the correlation and save like the highest peak. And this basically gives us the array response. Finally, the last set of experiments that we can run on Cosmos testbed is beam tracking measurements. So using again the channel sounding and the XY table, we can basically develop some kind of beam tracking measurements. So here we can see that one node is placed on both sides, and the other node is doing some kind of beam search, but it's also like moving. In this example, the mobility scenario is that the node is basically just rotates from -45 to 45 degrees. And this kind of rotation, it also stays in that position. So it goes like from -45 to 0, from 0 to 45, from 45 again to 0. So we can see that on the heat map on the right, we can see that we can actually like track the movement of the device, like the way it goes like from 0 to -45, from -45 to 0, and 45 and back to 0. So this is very important, and this enables us to do like this kind of like experiments. And as an extension to this work, we basically recently published a paper about using reinforcement learning on the Cosmos testbed for beam forming and for beam tracking experiments. If you want to learn more, you can basically check the WinTech in a few months. So thank you for your attention. We basically showed like some of the capabilities of the millimeter wave experimental platform at the Cosmos testbed, and we also showed you some of the possible experiments that we can run. And of course, you can try to think of your own experiments. And some of the tutorials, most of the tutorials are placed in this wiki, as we said earlier. And if you want to find the open source software code that we used to replicate and run this experiment, you can find it in this GitHub repository. First, I would like to thank the industrial affiliates of NYU, the NSF, and the SRC. And I would like to thank also you for your attention. If you have any questions, or if you want to get access to the beam tracking dataset, please feel free to email me. Thank you.